So hello everyone, today we'll be solving yesterday's div 3G. So the problem statement says there is a binary tree of n plus 1 vertices, n is odd, with vertices labeled 0, 1, so until n. At most one letter can be written on each vertex of the tree, and all vertices initially have nothing written on them. The root of the tree is vertex 0. That means, okay, I was trying to do this previously. Actually, this is the second recording. The previous one, due to some glitch, after I solved the problem, it got stopped automatically. Oh, okay, whatever. Yeah. So the tree would look something like this. 0, this would be 0, and 0 is the parent of 1, and rest all the nodes would have either 2 children or 0 children. So the tree would look something like this. Fine. Bob is lost in one vertex of the tree and wishes to escape the tree by reaching vertex 0. So 0 is the exit. 0 is the exit. This is very easy for most people with common sense. However, since Bob is an idiot, he created a new way of traversing the tree, introducing the idiot first search. When Bob is on vertex V, Bob's movement is determined as follows. If vertex V is a leaf, Bob always moves to the parent of V. Otherwise, check the next few conditions. If nothing is written on vertex V, Bob writes L on vertex V and moves to the left child of V. If L is written on vertex V, Bob overwrites it to R and moves to the right child of V. Okay. And if R is written on vertex V, Bob erases it and moves to the parent of V. It takes exactly 1 second for Bob to move to an adjacent vertex. So Bob will take exactly X seconds to perform X moves. Okay. Bob will take X seconds to perform X moves. And it has been shown that regardless of which vertex Bob starts on, Bob can reach vertex 0 in a finite amount of time. We don't know who proved it. Surely it can't be Bob, but it is definitely proven. If you're asked to answer Q queries of the following kind, VK, assuming that Bob starts on vertex V, determine the vertex Bob is on after performing exactly K moves. For each query, TV be the time taken to reach vertex V, then it is guaranteed that K is less than TV for every query. That means you can never reach to that particular exit vertex. Fine. So you can never reach that particular exit vertex. So looking at the constraints. Okay, keyboard's working. Fine. Looking at the constraints, I can say that I should be having a predefined path. I should be having a predefined path. It should be like a script or something, isn't it? It should be like a script or something. So if I trace the path out, if I'm starting from a vertex U, let's say, I would move to vertex L because U is initially nothing written on it. Nothing is written on vertex U. So I would move to L. Fine. I would move to L because if there was nothing written on it, you are supposed to move to L, isn't it? Bob writes L on vertex and move to the left side. Then I would complete, okay, this would take one move, and I would take way to left subtree because once again, there's nothing written on it. Even if I move to L, the upcoming nodes, there's nothing written on it. So I would complete the left subtree, which would take me, let's say, f of L time. And after this, after completing left subtree, can I say that the last thing I would visit would be a right one. The last thing I would visit would be a right one, isn't it? Let's say this is the tree. So it's 1. Nothing is written on 1. Go to left. Write L here. Go to left. Then nothing is written on 2. Right left. Go to left. Nothing is written on 4. Then you write left here. Then now something is written on 4. What is it? It's left. So you move to force right, which is indeed the parent. And it goes somehow like this. Okay, so how would the part look like? U, L, left subtree completed, then go back to U, then go to right node, right child, then go to right subtree, then again go to U, then finally maybe you can exit, isn't it? Okay, exit is never defined because K is always less than TV, so you can never exit from here. But I can say that this would take one move, this would take U to R would take one move, RS would take F of R, and finally U would take to reach here one move, and to reach here one move. Is that clear? So this would work like a continuous script. This would work like a continuous script. Okay, starting from here, this would work like a continuous script, isn't it? And can I say that this whole script, if you observe properly, is a Euler tool. This thing is a Euler tool, isn't it? This thing is a Euler tool. And even if you don't know this is Euler tool, you can still build this. I'm sure you can do this much of coding so that you can still build this without knowing this is a Euler tool. Fine, you can still build this. Okay, so one thing is very clear. We need to pre-compute the tool. We need to pre-compute the tool. We need to pre-compute the tool. And since I'm moving upwards, can I say that I'm doing binary lifting? Is binary lifting a good way to move upwards? Yes. So let's get started with the code. Fine. So let's get started with the code. What are our observations first of all? My first observation, I have a predefined script. My second observation, I can build this script. My third observation, I want to compute f of l, isn't it? I want to compute, sorry, not f of l, f of u. Some f of l, f of r, or something random f of u. What is this f of u? It is moves from u to exit. Sorry, not exit, actually parent of u. I want to compute f of u, which is nothing but moves from u to parent of u. Moves from u to parent of u. Is that clear? I want to compute this f of u because in between the script, there's a requirement of these things. So before actually jumping into the code, let us end this trouble with f of u first. So if it's this way, 1, 2, 3, 4, 5. Let us start from 1. So my path would be 1, 2, 1, 2, 4. It's same as the DFS path. But you would also backtrack. In DFS, backtracking is not possible due to the visited array. Okay, because you store the visited nodes, the backtracking is not possible. But in this case, we need backtracking because this is not DFS. This is idiot first search. So 1, 2, 4, 2, 5. 1, 2, 4, 2, 5. Then again 2. 1, 2, 4, 2, 5. Then 2, then 1, then 3, then again 1, then exit, which is 0. This would be the path, right? This would be the path. So if my u is 4, f of u for 4 would be 1, isn't it? F of u for 4 would be 1 because I can directly reach the parent. And for 5 also, I can directly reach the parent within one move. Isn't it? So for 5 also, f of u would be 1. Coming to 2. Let's compute f of 2. This node. Parent of 2 is 1. When can I reach 1? First I need to visit 4, then I need to visit 5. So I need to visit 4, I need to visit 5. Then again, 4 would visit 2 and 5 would visit 2. Then in the fifth move, I can visit 1. So if I take the contribution of every node, the contribution of every node is 2 times. The contribution of every node is 2 times, isn't it? The contribution of every node is 2 times. And can I say that this would be equal to 2 into size of subtree. 2 into size of subtree minus 1. Can I say that? Because the size of this subtree is 2. The root of the subtree would contribute only once. It won't contribute twice, isn't it? That's why we are doing a minus 1. Is this part clear? And this would give you f of u. Is this part clear? So now we have a predefined path. And also we know how to compute moves for this path using this f of u formula, size of subtree minus 1. So I have this f of u also. Now I should get started. Fine. So what was my first step? My first step was doing a DFS traversal, isn't it? Because the movement was a replication of DFS. The movement was a replication of DFS. So I would do a DFS traversal. Before that, I would like to have some pre-computations, which is, okay, for binary lifting, let's take a first constant. Okay, what was the question's constraints? N was supposed to be this. Also take a constant log. 20 should be enough. 20 should be enough. All these things are for binary lifting. And R of size n. And parent also of size n. These are the three possibilities, right? Either you can go to L or R or parent. And we need to compute the formula F 2 into subtree size minus 1. So F would be of size n and Sz also of size n. And we will need this for binary lifting. Sorry, not down. What am I typing? Distance. And we are storing 2. Okay. So let's do the DFS part first. Forget it's a Euler tool. First thing, forget it's a Euler tool. Forget it's a Euler tool. Okay, size of U is initially 1. And parent of U is initially P. If left of U exists, then you do DFS. Is this DFS clear? Is this DFS clear? Okay, is this DFS clear? If there's left of U, you're doing the same thing. It's like the same order, isn't it? It's the same order. And with this, you can compute F of U, which is 2 into size of U minus 1, the formula which we just derived. Now we need to build that particular tool. So let's write a build function. Forget it's a Euler tool. Okay, let's take this in of U equal to 2 dot size and 2 dot push back U. If there's L of U, then build it for the left subtree, then for the right subtree. Okay, build it for the left subtree. And then build it for the right subtree. And after starting any subtree, before starting any subtree, you would visit the parent, isn't it? Sorry, after ending every subtree, you would visit the parent also. So once again, you would do 2 dot pushback U. Okay, with this, the tour would be built. Is that clear? What are we exactly trying to build? We are trying to build this order. 1, 2, 1, 2, 4, 5. Then for 2, 4, once you complete 4, once again you're pushing the parent 2, then you're going to 5, then once again you're pushing the parent, then you're completed with this particular tree, this particular subtree, 2, 4, 5, everything is completed. Then you're going back again, pushing 1, then 3 completed, again you're pushing back 1, then 0. Okay, so this is how it works. Alright, fine. You're building the exact same tool. Okay. Now, let's take the input in M, Q, and I less than or equal to n, I plus plus. Okay, you would do this DFS first, starting from 1. One's parent is 0, right? One's parent is 0. And you would build this tour first, starting from 1. And since at last you need to push back a 0, let's do it here. Let's do it here. Let's push back that 0. Vector in, sorry, why am I typing this again? 2 dot push back 0. Okay, 2 dot push back 0. Now it's time to move upwards by doing binary lifting. Okay, binary lifting is a very simple thing. There are many resources you would find. Gradually I would also do a video on this, but this is not the right time to learn binary lifting because this problem is something that involves binary lifting. It involves it. You should practice some more generic problems before this. This is if this is the first time you're touching binary lifting, this is not the one I would prescribe you to do. So int I equal to 1, I less than or equal to n, I plus plus. Fine. Now coming to the queries part, let's take the queries. C in B K, if K is greater than or equal to B, sorry, K is greater than or equal to f of V, K minus equal to f of V, V equal to parent of V. Okay, with this we have finished the initial vertex. We have finished the initial vertex, isn't it? We have finished the initial vertex. And if V is not equal to 0, we are trying to jump. We are trying to jump through fresh ancestors, isn't it? For int j equal to log minus 1, j greater than or equal to 0, j minus minus. If up of V j, which we obtain from binary lifting, if it's a non-zero thing, and k is greater than or equal to distance of Vj, k minus equal to distance of Vj, and V equal to up of Vj. Okay, with this we are moving upwards, and finally you are left with this thing. If V equal to 0, else you will see out. Now you know the order, right? Now you know the order. Like if you are ending at kth move, you know where are you standing at the end, because the tour is already pre-computed. You just need to access this particular index. Okay, you just need to access this particular index and it would give you the answer. Fine, let's test this out. Hope doesn't give a compilation error. Okay, fine, passed. Let's submit this. Done. Accepted. So that's it for today. I hope this concept was clear. The main thing is, main thing you gain from this problem is neither the Euler tool, obviously you can add it to your toolkit, undoubtedly, but this problem basically teaches you how to observe constraints and come to decisions like, um, okay, I cannot backtrack always. With these constraints, I cannot backtrack always. Is that clear? I cannot backtrack, right? Keeping these constraints in mind, I can never backtrack. I can never find out the actual path just by doing some sort of a simple DFS. I have to pre-compute some sort of thing. I need to pre-compute a path so that I can return it. And the mind usually shifts to observing the path, which is very natural. So it's something very trivial, right? If you're sure that you need to pre-compute something, you would start observing it. That's what I did. And forget it's a Euler 2. Forget it's a Euler 2. Forget this thing even exists. What are you doing? You're just implementing the way to move to this path. You're just implementing the way. First thing, you're pre-computing this because you came to know, okay, I need this. Okay, so the strategy itself is totally need based. You're doing what you need. And this tool building part, all this stuff is very trivial, right? It's very trivial. You observed the path and you just came to conclusion that this is what you should be building. And later everything, yeah, okay, this binary lifting thing was something you should have known. But even if you just make a simple search on your browser, like how to move upwards or something like that, if your search terms are very close, this would be the first link that would open, obviously, and you can learn it in between the contest also. All right, it's not considered cheating anyways. Okay, if you're learning it and then implementing in between a problem, which is a pre-existing technique. Okay, so these kind of things are learnable. You just need to know what you're doing. You want to move up, just find a way, just find an algorithm that exists, or maybe some technique that exists. Okay, so and processing the queries, it's just, if you have figured it out till here, there's nothing to worry about. Okay, with little bit of practice, you can actually figure out these kind of techniques and you can apply them and reach here. So for some people, these things may not be trivial. There are some other techniques also which are pretty advanced. There's something known as heavy light decomposition, which requires a segment tree. We would talk about it some other day. Maybe tomorrow itself I would be glad to tell. And also, if you feel that this binary lifting is an overkill, you can use a stack also. That also we'll discuss on some other day. We can use a stack also. But there's one condition, you need to be implementing a searchable stack. Okay, searchable stack. What's a searchable stack? It's very simple. It's just stack using arrays. Okay. It's in very basic textbooks, stack using arrays. It's also known as a searchable stack because in between you can just apply a binary search or something like that. So it's a benefit of implementing stack with arrays. Most people are just like, okay, I would implement this using HTL or something else. But no, this is a pre-existing concept called searchable stack. And it's been there always. Okay, so never underestimate some basic textbooks which says you might be like, okay, with linked list it's more optimal or something is more optimal. YouTubers may tell you, but they don't know this technique actually exists. Some people who say linked list one is more optimal, they don't even know this thing exists. Okay, so we'll be discussing all this stuff, heavy light decomposition on the same problem and again on the same problem. Okay, and also the searchable stack thing. We'll be discussing it very soon, maybe tomorrow itself. So thank you everyone.